Hello guys, and welcome back to our networks related lectures. My name is Yurii Babich. I work at Odessa National Academy of Telecommunications, and today we're gonna be talking about OSI reference model. But before actually getting to this topic, let's clarify why you should be aware of this model, so why it is so significant. Basically, it doesn't matter whatever you do, you can troubleshoot a network, you can design a network, manage network, whatever, your actions will be expressed in terms of that model. So it's a very, very basic knowledge of networking, so let's get to it. But before the actual model, let's start from a little bit of history. The first networking solutions were available from IBM, DEC and ArcNet, but they were absolutely proprietary. So if you had IBM, you could interwork with IBM, DEC with the DEC, and the same for ArcNet. So no internetworking at that point. Even later, with the products from Novell and Apple, like AppleTalk, there was no internetworking. So if you had a computer from Novell and from Apple, the only way to transfer data was to take a floppy disk, copy data on it, and move between computers. So that led to the necessity of working out the general model that will be compulsory for all the equipment manufacturers, for software developers, for everyone involved in networking. So let's take a look at the turning points in working out such a model. In 1977, ISO, the International Standardization Organization, came out with the first draft version of its 7-layer model. In 1989, University of California, Berkeley released TCP/IP code for the public, and since that time everyone could use TCP/IP. Then in 1992 Windows 3.11 had TCP/IP functionality on board. And finally in 1994 ISO and ITU, International Telecommunication Union, came up with their international recommendations, documents specifying the 7-layered model. You see it here. So 7 layers from physical to application. Now let's take a look at several questions. First, why layers? So why it uses layered approach? So the layer approach gives us enough granularity to modify protocols residing at every layer in the manner that not to affect adjacent layers. So if we modify, let's say, network protocol, it won't affect transport or data link. So here you see the correspondence of 7-layer model to TCP/IP model. By the way, TCP/IP model is described in RFC 1122. So let's take a look at functionality residing at every layer. By the way, that functionality is implemented by the protocols. A protocol is a set of rules for operation. Now let's start from the application layer. So the main task of the application layer is to enable our applications to use networking infrastructure, to make it talk to the network. And here we see the protocols that support our applications like DNS, HTTP, FTP, email protocols, Telnet, SSH, DHCP. So all these protocols support operation of our applications. So all that actually is done to support the application, to make us use the applications. Now, let's take a look at the presentation layer. There are 3 functions performed at the presentation layer. These are data encryption, data compression, and data representation in terms of converting formats. So the presentation layer must present the information in the form that would be understandable to the applications. And here we see the protocols like MPEG, JPEG, PNG, TIFF, GIF, and here we see several protocols involved in encryption, SSL and TLS. Now let's move to the session layer. The task of a session layer is to enable applications to talk to each other, to have the dialogue. For example, one application may authenticate another application, and that is done by the tools included at the session layer. These tools are APIs. API is a set of commands available to a software developer to implement the functionality of software. So here we also have TCP/IP sockets. We have Windows sockets, etc. Socket is actually a combination of IP address and the port, and we're going to talk about that a little bit later. Now let's get to the next significant layer, which is the transport layer. So the basic task of a transport layer is to deliver data from application to application. To actually complete this task, transport layer must address applications somehow, because you can run different applications at the same time on your PC, smartphone, iPad, etc. So, for example, you are running Viber, Facebook, Google Chrome, and information intended to Google Chrome shouldn't get to Facebook or to Viber. So that requires addressing. An address entity at the transport layer is called a port. So there are TCP ports, UDP ports, so the port is the address that allows correct data delivery, and it actually resides at the transport layer. Now, the next significant function of a transport layer is segmentation. Let's take a look at a simple example. You're downloading the movie. Let's say the movie takes approximately 5-7 gigs, and there is no possibility to push such a huge file through the network as one piece. So this initial message, the movie, should be broken into segments, and those small segments will travel across the network. And this segmentation is performed by the transport layer. Every protocol actually operates with a so-called protocol data unit. Protocol data unit is the portion of information with appropriate header of corresponding protocol attached to it. And the protocol data unit, or PDU, of the transport layer is a segment. Now, here we see another significant concept to understand. It is encapsulation. So, what is encapsulation? Encapsulation means that data coming from upper layer is put inside the protocol data unit of underlying layer. So here we see data coming from application layer is encapsulated into a UDP segment. UDP segment is encapsulated into IP packet, and IP packet in its turn is encapsulated into Ethernet frame. That is encapsulation. The reverse process is called decapsulation, when we extract data layer by layer from the protocol data units. Now let's Let's continue with the transport layer, and let's discuss the rest of functionality and rest of protocols we can see here. So, TCP and UDP protocols that have been here for ages, so they are quite old protocols. TCP actually provides reliable data transmission, so it establishes logical connection before transmitting anything, It tracks the segments, it can identify the lost segment, it can retransmit the signal, so it is reliable, but the downside is that it operates slower compared to UDP. UDP doesn't establish connection, doesn't maintain the right order of segments, but it operates faster compared to TCP. And the new protocol designed by Google is QUIC. QUIC is supposed to replace TCP at some point, but actually in modern networks they operate together. So what is the idea behind the QUIC? The typical protocol stack for, let's say, web surfing looks like this. We have HTTP at the application layer, TLS at presentation, TCP at transport, and then IP at the network layer. So during actually data session, there should be two handshakes. TCP requires handshake to establish the session, and TLS requires handshake to establish the session. In the case of QUIC, only one handshake is required. So it actually saves time, and here we see that it takes twice less time to establish the connection, because QUIC actually requires only one handshake, and it includes congestion control functionality and encryption. And pay your attention that QUIC resides on UDP. UDP provides less overhead compared to TCP. It has smaller header, so less service data is transported in this case. Now, let's move to the layer where actually internetworking happens. It is network layer. The task of a network layer is to transport data between networks, from sender's network to a recipient's network. To do so, actually, it must perform two functions. First, actually data transfer, and that is done by the protocols like IPv4, IPv6. IP is Internet Protocol. So the first function is data transfer, and it is performed with the help of IP packets. But the second function is called routing. Routing is the process of selecting the best route from sender's network to a recipient's network. Routing is performed by network equipment called a router. So here we have marking for a wireline router, for wireless router, but actually it doesn't matter which technology it uses, but it performs the same task. It unites networks. It ensures data transfer from one network to another network. Now, and here we see the routing protocols like OSPF, BGP, EIGRP, RIP. So all these are the routing protocols. Now let's move to the next slide, and here we have a data link layer. The basic task of the data link layer is to enable communication within a network. So the task of the network layer was to enable communication between networks, but at the data link layer we have communication within one network. So to support the communication between computers or nodes, any kinds of nodes within a network, we need addressing scheme. And address at the data link layer is actually called physical address, and in the case of Ethernet technology it is the MAC address. The next function is framing. So a frame should be created at this layer. So a frame is a portion of data received from the network layer with appropriate service data, the header, attached to this data. Now, the next function performed at this layer is error detection, and if the technology supports, error correction. By the way, Ethernet only supports error detection. Now, let's take a look how the data link layer looks like in the case of Ethernet. It is divided into two sublayers, logical link control and MAC, medium access control. The task of a logical link control is to receive data coming from network layer, precisely IP packet, to mark which protocol should be processing the data at the receiving side, and the rest of the job is done by the medium access control sublayer. So it accesses the medium, it creates frames, it checks for errors, so all the rest work is done by the MAC. To enable communication within a network, switching should be performed. So switching, it's a data distribution within local area network, and this function is performed by a device called a switch. Now let's move to the physical layer. Basically, the task of a physical layer is to take binary data from the data link layer and push it to the transmission medium. There are three kinds of transmission medium. First one, fiber optical cable. Second one, copper cable. And third one is air for wireless communication. To perform this function, physical layer basically does three functions. First one, coding. Coding is required to protect the binary data from all kinds of disturbances along the path between points A to B. The next function is the parallel to serial conversion. So, computer may operate in a parallel manner, but transmission is usually happens in a serial manner, so parallel to serial conversion is required, and it is usually done by a network card. The next function is a signal transmission and emission. So, the network card of your computer must somehow emit the signal either by LEDs, lasers in the case of fiber optics, or using RF antenna, etc. So it should emit a signal somehow. Now let's continue with the physical layer. Guys, the physical layer can be the most expensive part of your network. So here we see the map of submarine cables connecting Europe and United States. So these are the elements of the physical layer. Here we see antennas of the base station, so it's also a part of a physical layer. The most scientific effort is actually aimed at the physical layer. Organizations like ITU focus their attention at the technologies of the physical layer. Now, let's take a look how actually our OSI model relates to the real life. So it's not just the blocks with the signs, no. It actually corresponds to real life somehow. Let's find out how exactly. So here we have a pretty simple communication scheme. We have a computer, switch, router, and this is one network, because I hope you remember that a router connects different networks. And here on the right we have another network with a switch and another computer. Let's consider a situation when that computer sends a file to this computer. So what happens? Actually, at the application layer, we have protocols that support the application that allows us to send the file. Then it goes to presentation layer, so it goes from top to bottom. Encapsulation happens. So it goes to transport, it is encapsulated to, let's say, TCP segment, then TCP segment is encapsulated into IP packet is encapsulated into Ethernet frame in the form of electromagnetic pulses is sent to the switch receives the data frame, actually it receives the set of electromagnetic pulses, so it identifies the binary data, singles out the Ethernet frame and checks the header. It understands where to forward this frame. It forwards to the switch. The switch decapsulates till the IP packet, checks the IP header and identifies where to send that IP packet, and then it creates new frame. The IP packet is encapsulated into this frame and then sent out to this network. Switch receives this frame, does the same job as before, and forwards this frame to this computer. Computer receives the frame through the physical layer. At the data link layer, the frame is singled out, so the binary data is obtained. Then IP packet is decapsulated and provided to network layer. TCP segment is decapsulated and provided to the transport layer, and then the data is provided to the corresponding application. So guys, you have to understand this model. And for example, in the case of troubleshooting, if we have some cabling issue here, then we're talking about the physical layer issue. If we have some problem with a network interface card, then we're talking about data link layer issue. If we have some sort of IP address misconfiguration, then we're talking about the network layer issue. But let's assume a situation that a file should be transmitted, but you cannot transmit it, and you try to troubleshoot the problem. Why you cannot transmit the file? So if you ping this computer from that, and the ping is successful, you can conclude that the first three layers operate correctly, and the problem is somewhere at the layer that is over the network layer. Probably your firewall is configured incorrectly. So this is how the OSI model relates to the real life and our day-to-day job. Alright guys, thanks for your attention. Please, if you have any questions, write them in the comments below the video. I will answer them. See ya.